Hello my friends, and welcome back to Sky Creative Channel. From molten steel glowing at 3,000 degrees to precision machinery that builds the railroads carrying America's freight, today we're taking you inside 5 of the world's most incredible manufacturing facilities. Let's get started. Our first stop brings us to Austria, home of voestalpine AG, a company whose roots stretch back over 160 years to 1938. This isn't just any steel company. It's a global powerhouse that has revolutionized how we think about steel pipe manufacturing. What makes voestalpine special? They've mastered the art of creating seamless steel pipes that are so precisely engineered. They're trusted in everything from oil drilling operations in the North Sea to power plants across America. Let me paint you a picture of what we're about to witness. Imagine transforming a solid block of steel into a perfectly hollow tube without a single weld or seam. It sounds impossible, doesn't it? Yet voestalpine has been perfecting this process for decades, and today we'll see exactly how they do it. NTHE's story begins at voestalpine's Stahl Donawitz, their primary steel production facility. Here, raw materials, iron ore, coal, and recycled steel are transformed into high-quality steel billets through their state-of-the-art continuous casting process. These aren't just any billets. They're precisely engineered starting points, each one heated to an exact temperature of 200 degrees Fahrenheit. Think about that for a moment. That's hot enough to melt copper. Now comes the magic. These glowing hot billets enter what's called the cross-rolling mill, the first of 3 critical shaping stages. Picture a massive machine with rollers positioned at angles to each other. As the billet passes through, these rollers don't just flatten it. They begin to create a hollow center through intense pressure and rotation. The engineering behind this is remarkable. We're talking about forces equivalent to the weight of several locomotives, all focused on gradually opening up that solid steel. NBUT were just getting started. The partially formed pipe now moves to the pusher mill, and this is where things get really interesting. Imagine a mandrel, that's a precisely shaped metal rod, being pushed through the center of our heated steel while additional rollers work the outside. It's like threading a needle, except the needle is white-hot steel, and the thread is a precisely calibrated mandrel that's harder than the steel itself. This process stretches and shapes the pipe, creating the exact internal dimensions required. NTHE's third and final major stage involves the stretch-reducing mill, and this is where precision meets artistry. Here, a series of rollers, sometimes up to 20 pairs, gradually reduce the pipe's diameter while extending its length. Each roller is positioned with tolerances measured in thousandths of an inch. The pipe passes through at speeds of up to 25 miles per hour, yet the dimensional accuracy achieved is astounding. We're talking about variations so small they can barely be measured. What's fascinating is that throughout this entire process, the steel never cools below 800 degrees Fahrenheit. The timing is critical. Too hot, and the steel becomes unworkable. Too cool, and it becomes brittle. The operators monitor dozens of parameters in real time, making micro adjustments that would have been impossible just a generation ago. NBUT, here's where voestalpine really shines. Customization. Depending on the customer's needs, pipes might undergo additional processes. For oil and gas applications, they might receive specialized heat treatment to enhance their strength. For power generation, they might get precision boring to create ultra-smooth interior surfaces. Some pipes destined for chemical plants receive special coatings applied at the molecular level. NTHE quality control process is something to behold. Every single pipe undergoes ultrasonic testing, sound waves that can detect flaws invisible to the human eye. They use eddy current testing, magnetic particle inspection, and hydrostatic pressure testing that subjects each pipe to pressures far exceeding what they'll ever encounter in service. What we're witnessing here isn't just manufacturing. It's the culmination of over a century of metallurgical knowledge, combined with cutting-edge technology. These seamless steel pipes will find their way into projects across the globe, from the Alaska pipeline to offshore drilling platforms in the Gulf of Mexico, each one a testament to the precision and expertise that makes modern industry possible. Our journey through modern manufacturing now takes us to Germany, where we'll explore a process that literally keeps our trains on track. Meet Vollert on Lagenbau, a company that's been engineering precision since 1925, and their remarkable system for producing Leonhard-Moll concrete railroad ties. You might wonder why we need concrete ties when wooden ones served railroads for over a century. Well, here's a fascinating piece of railroad history. Wooden ties, while traditional, typically last only 7 to 10 years under heavy freight traffic. Concrete ties, on the other hand, can serve faithfully for 50 years or more. That's not just economics, it's engineering evolution. NTHE process begins with what Vollert calls their recipe for perfection, a carefully calibrated concrete mix that's far more sophisticated than what you might imagine. We're not talking about sidewalk concrete here. This specialized mixture includes Portland cement, precisely graded aggregates, and chemical admixtures that control everything from setting time to ultimate strength. The concrete achieves a compressive strength of over 8,000 pounds per square inch. That's strong enough to support a loaded freight train traveling at 80 miles per hour. And watch as the automated batching system measures each component to tolerances of plus or minus 1%. The mixing process itself is a marvel of precision timing. High-intensity mixers blend the materials for exactly 90 seconds, not a second more or less. Too little mixing and the concrete won't achieve uniform strength. Too much, and you'll introduce unwanted air bubbles. Now comes the heart of the operation, the pre-stressing system. Before the concrete is even poured, high-tensile steel wires are stretched along the length of the forming bed under precisely controlled tension, typically around 28,000 pounds per square inch. This pre-stressing technique, pioneered in Europe in the 1940s, is what gives these ties their incredible durability and resistance to cracking. NTHE concrete pouring process uses a sophisticated distribution system that fills each tie mold uniformly. What's remarkable is watching the vibration process. Powerful pneumatic vibrators eliminate air pockets while ensuring the concrete flows around every detail of the reinforcing steel. The frequency and amplitude are precisely controlled. Too little vibration leaves voids. Too much causes the concrete components to separate. Here's where Vollert's engineering really shines. Their steam curing chambers. These massive pressure vessels subject the freshly molded ties to carefully controlled heat and humidity cycles. Over 8 to 12 hours, the temperature gradually rises to 185 degrees Fahrenheit while steam maintains optimal moisture content. This accelerated curing process allows the concrete to achieve in hours what would normally take weeks. NTHE demolding process is particularly impressive. Hydraulic systems lift entire sections of the forming bed, and you'll see dozens of perfectly formed ties released simultaneously. Each tie emerges with mounting points pre-formed for rail clips, precise dimensions that ensure perfect track gauge, and surface textures designed for optimal ballast retention. Quality control happens at multiple stages. Concrete samples from each batch undergo compression testing, and finished ties are subjected to load testing that simulates decades of service in just minutes. Some ties are tested to failure, and the forces required are truly impressive, often exceeding 100,000 pounds before cracking occurs. NTHE final step involves aging. Yes, concrete actually gets stronger with time. These ties are stored in carefully controlled conditions for 28 days, during which the concrete continues to cure and strengthen. By the time they're ready for installation, each tie represents a perfect marriage of materials, science, and precision manufacturing. What we're seeing here isn't just concrete work. It's the foundation of modern transportation infrastructure, engineered to support the massive freight trains that keep America's economy moving. Welcome to perhaps the most impressive engineering project you'll witness today, the complete construction of a modern railway system. Our partners at Structuralia are about to show us how 21st century railroads come to life, from the first shovelful of earth to the moment that first train rolls down the track. And railway construction today is nothing like the railroad building of the 1800s. While those pioneering railroad builders relied on muscle, dynamite, and determination, today's projects combine satellite-guided precision with massive machinery that would seem like science fiction to those early engineers. Let's start with excavation, and this is where modern technology truly shines. Those massive excavators you're seeing aren't just digging randomly. Each machine is equipped with GPS systems, accurate to within inches, following digital terrain models created by laser scanning drones. The lead operator is essentially following a three-dimensional blueprint projected right into his cab display. Watch those articulated dump trucks. Each one can carry 45 tons of material, and they're following predetermined routes optimized by computer algorithms. What's remarkable is that every cubic yard of soil has been analyzed and categorized. Some will be used for embankments, some for backfill, and problem soils will be removed entirely and replaced with engineered materials. Now we come to one of the most challenging aspects: bridge construction. Modern railway bridges must support loads that would have been unimaginable to earlier generations. A single freight train can weigh over 15,000 tons. That's like 150 blue whales rolling across a structure at 70 miles per hour. NTHE Bridge, you're seeing, constructed uses precast concrete segments, each one precisely engineered and manufactured off-site. Watch as the massive crane, a 500-ton capacity mobile unit, positions each 40-ton segment with millimeter precision. The engineering tolerances are astounding. These segments must align perfectly, with gaps measured in fractions of an inches. Tunnel construction presents entirely different challenges. The tunnel boring machine, or TBM, is essentially an underground factory. As its cutting head, over 30 feet in diameter, chews through rock and soil, it simultaneously installs concrete lining segments and monitors ground conditions ahead. The operators work in a pressurized environment, and every aspect of the operation is monitored from a central control room that looks more like a space mission command center. But here's where railway construction gets really interesting: the track installation itself. Those rails aren't just placed on top of ballast like you might imagine. Modern continuous welded rail comes in quarter-mile sections, delivered by specialized rail cars and installed by machines that can lay over a mile of track per day. NTHE ballast, those crushed stone pieces beneath the track, isn't random gravel. It's precisely graded granite or basalt, sized to provide optimal drainage while maintaining stability. Watch as the ballast distributors spread exactly 18 inches of material, followed by tamping machines that use hydraulic tools to pack the stone around each tie, with over 60,000 pounds of compacting force. End signal system installation represents the nervous system of the railway. Those signal masts you see being erected will communicate with trains using both traditional electrical circuits and modern positive train control systems. Each signal location is surveyed to GPS coordinates, ensuring trains receive the right information at precisely the right location. NFOR electrified railways, we enter an entirely different realm of complexity. The catenary system, those overhead power lines, must maintain constant height and tension despite temperature changes, wind loads, and the dynamic forces of trains passing beneath at high speeds. The support structures are engineered to withstand forces equivalent to Category 3 hurricane winds while maintaining electrical clearances measured in millimeters. NTHE final phase involves comprehensive testing that would impress any quality control expert. Geometry cars traveling at track speed measure rail alignment, gauge, and elevation to tolerances of a quarter inch. Dynamic loading tests subject the completed track to forces exceeding those of the heaviest trains it will ever carry. What's truly remarkable is how all these systems work together. The excavation must be precise enough for the bridges must align perfectly for the track must be perfect for the signals, and the signals must integrate seamlessly with the power systems. It's a symphony of engineering precision that represents over 2 centuries of railway development compressed into one remarkable construction project. Our industrial journey now takes us to the heart of European steel production, where Nova Hut continues a steelmaking tradition that spans generations while embracing the most advanced metallurgical technologies of our time. And steel production is one of humanity's oldest industrial processes, yet what we're witnessing here would be completely unrecognizable to the blacksmiths of just 150 years ago. The scale alone is breathtaking. Where a traditional blacksmith might work with pounds of metal, Nova Hut processes hundreds of tons in single batches. NTHE process begins with raw materials that tell a story of global supply chains. Iron ore from places like Australia and Brazil, coking coal from mines across Europe and North America, and recycled steel scrap that gives new life to everything from old automobiles to demolished buildings. Each material is tested and analyzed before it ever enters the facility. And watch as these materials feed into the blast furnace, a towering structure that's essentially a controlled volcano reaching temperatures of 3,000 degrees Fahrenheit. Hot air, preheated to over 2,000 degrees, is blasted into the base of the furnace, creating a chemical reaction that separates pure iron from the ore. What emerges is molten iron so hot it glows white, flowing like water into massive ladles. NBUT. This is only pig iron, useful, but not yet steel. The transformation happens in the basic oxygen furnace, where pure oxygen is blown onto the molten iron at supersonic speeds. This process removes excess carbon and other impurities, and the precision required is remarkable. Too much oxygen and the steel becomes brittle, too little and it remains too high in carbon content. NTHE chemistry happening here is fascinating. Skilled furnace operators, modern alchemists really, add precise amounts of alloys. Chromium for corrosion resistance, nickel for strength, manganese for hardness. Each heat of steel is like a carefully balanced recipe, with ingredients measured not in teaspoons but in tons. Temperature control throughout the process is critical. Pyrometers and thermal imaging systems monitor the molten steel constantly, and operators can adjust the heat within degrees. The steel must be hot enough to remain fluid but cool enough to prevent damage to the furnace lining, a delicate balance maintained through decades of experience and modern technology. NTHE casting process showcases precision manufacturing at its most impressive scale. Continuous casting machines transform the molten steel into solid billets, blooms, or slabs in one continuous operation. As the steel solidifies, it's cut to precise lengths by automated torch systems that move with robotic precision. Quality control happens throughout the entire process. Spectrographic analysis provides real-time chemical composition data, while ultrasonic testing reveals internal structure details. Each batch of steel receives a birth certificate, documenting every aspect of its production, information that might be referenced decades later when the steel finds its way into bridges, buildings, or manufacturing equipment. What we're witnessing isn't just manufacturing, it's the foundation of modern civilization. The steel produced here will become the skeleton of skyscrapers, the hulls of ships, the framework of factories. Each glowing ingot represents centuries of metallurgical knowledge applied with 21st century precision. Our final stop takes us to China, where Jiangsu Shuguang Group demonstrates one of the most specialized steel manufacturing processes in the world: the production of drill pipes for the global energy industry. Drill pipes might not sound glamorous, but these specialized steel tubes are the lifelines of oil and gas exploration, capable of reaching depths of over 30,000 feet beneath the Earth's surface, while withstanding pressures that would crush ordinary steel. NTHE process we're witnessing is called upset forging, a technique that thickens the ends of the pipe to create starting with seamless steel tubes ranging from 2 3/8 inches to 8 5/8 inches in diameter. Each pipe must be precisely heated to 950 degrees Fahrenheit, hot enough to make the steel malleable, but not so hot as to damage its crystalline structure. And watch as the automated heating system brings each pipe end to the exact temperature required. Infrared sensors monitor the heat distribution, ensuring uniform temperature across the entire circumference. This precision is critical. Uneven heating would create stress points that could fail thousands of feet underground. What makes this process truly impressive is the consistency required. Every drill pipe must meet the exact same specifications, because in a drill string stretching miles into the earth, each pipe depends on every other pipe for the integrity of the entire system. The precision manufacturing we're witnessing ensures that whether you're drilling in the Texas oil fields or the North Sea, these pipes will perform flawlessly under conditions that challenge the very limits of material science.